Okay, so we have some people missing today, but we are going on to talk about two things today. I put on Google Chat one link to a video called the Boltzmann distribution curve. So you can go there and get that link open. I'll put it here for the benefit of you, Aditya, on the board. And the other thing is to FET simulations. So I want you to go and open up your FET simulations, and also the another tab, open up the what do you call it, Maxwell-Boltzmann curve. Okay, I have both of them open.
So where's the Maxwell-Boltzmann curve?
Maxwell-Boltzmann curve is a link on Google Chat. Also, I mentioned about both of these things on Toddle. Maxwell-Boltzmann curve is, for people watching online, you will see there's a link on Google Chat, and with that link on Google Chat, it will open you up here to the Maxwell-Boltzmann curve, which I'm going to explain a little bit about today, and how this Maxwell-Boltzmann curve connects to what we spoke about in the last class, which is temperature. Who remembers the definition of temperature? Any of you guys here remember what we say temperature is?
So it is the average heat distributed among the particles.
Average heat distributed among the particles. Okay, so you could have, let's compare it to two classes. You could have one class where the average is 60, another class where the average is 80. Does that mean that the people in the class averaging 60 have all scored, every one of them have scored less than the class that averages 80? What do you think? What do you think about that, Aditya? You following that, what I'm saying?
Yeah.
What? So if you are in the class that scored less, does it mean that everybody in the other classes have beaten you?
No.
What it means?
Average means like
Someone got more, someone got less, so it's a midpoint.
Yeah. Now, if I ask you, which class is more likely to have the topper? Which one would you bet on? 80, right? Statistically, that is the one that, okay, it's averaging 80. Maybe the person who got 100 over 98 is in that class. It's more likely.
Yeah.
But it's very possible that it could be in the other class also.
Yeah.
Okay? If I tell you that the topper is in the class that averages lower, and then I ask you to predict which class has the lowest performer, what would you go for? 60, because if they have the topper and they're still averaging 60, it means it's a chance that they also got the bottom, the person who scored like 10 or 12 or something, right? That might be in that same class also, and then it just cancels off the two sides and it comes down, and then the other people are all distributed. So this is like very much like two temperatures. That example is very much like two temperatures, which we are going to talk about today. But the Boltzmann curve will only be meaningful when we take a look at another thing that we have been collecting data on, which is, what two types of reactions have we been collecting data on over the last? Exothermic and endothermic. This is meant to represent one type of reaction that we have studied last time, or possibly both types of reactions. If I said it represents one type of reaction that we studied last time, one word, what would be the one word to describe it? Exothermic. Okay, Aditya. Asta, you're seeing why he's saying that word? You're seeing the simulation. But he's saying exothermic when he sees this. You see any reason why he's saying that?
Because the temperature of the thermometer rises.
Temperature of the thermometer rises. Okay. What about you? Are you guys realizing something here?
Yeah, there's a rise in the
That is the exothermic graph.
That's the exothermic graph. Now, are you sure that this is exothermic graph? 100%. I mean, it looks, I understand you're seeing the shape, but what information do you have to say it's exothermic? What information? Because you know there's the other word.
temperature rises.
Temperature rises, well, okay, temperature rises, yes. If it's exothermic, temperature will rise. How do you know temperature is rising, and what's the other type of reaction that we studied? Endothermic. So what information do you have here to say that this is exothermic or endothermic or anything like that? Do you have any information? We call this the reaction coordinate, the progress of the reaction, and kinetic energy up here, right?
Yes.
Well, actually, I think they say, some books say potential energy. We just write energy. So, which side is products and which side is reactants?
Left side is reactants, right side is
Well, that is usually like what we see all over, right? That's reactants. and that's products. So then because we see this all over, we assume that this is the case also. Okay? It's sort of like if you see this marker, and because of you know all about markers, you assume that the way to open it is to pull this open and you'll get the felt side here. But suppose somebody decided to make a trick marker, and as you pull it like this, the part to write with is here, and all of this is the cover.
Yeah.
You think somebody could make a marker like that?
No.
They can't make it at all. They wouldn't make.
But
Why can't they make it?
How will they store the ink if that?
They're going to store the ink, and they're making it deliberately as a trick.
That
So,
would be a marketing strategy.
you imagine.
It could be like hollow and
No, you imagine Asta, you make a marker like that, when this is the part to write with and all of this is the cover. And you give it to a teacher, a whole box like that, right? And you put a hidden camera in the room. And nobody's watching, the teacher comes and this. I think the teacher would say when they do that, it would be priceless to get the the look on their face and hear what they say. So haven't you seen like any movies or videos where people are deliberately putting a hoax like that?
Yes.
Well, the nice people at the IB, they like to do that to you guys as well. So sometimes they will ask you, what is the energy associated with the reverse reaction here? Is that confusing to you?
No.
Is the reverse reaction exothermic or endothermic?
Endothermic.
Endo.
What do we mean by the reverse reaction?
The reverse of what is happening.
It means you have to look at this thing that way.
Yes.
So therefore they will give you a graph looking like this in the exam.
Yes.
And then they will ask you, they wouldn't tell you reactants and products. They would say this graph represents A plus B, and then they do this. What is this representing?
Reverse.
Reversible.
Both sides.
Asta, you have seen this arrow ever before, like this, one going this
Yes.
way? And even if you haven't seen it, you can understand why it means reversible.
Yes.
Right? It's kind of like lots of times on boxes that people use for shipping, like things internationally, they would have a sign written this side up, but they'll have a drawing also of like something to show you like how to place the object, like this side at the top and this side at the bottom. Or they might have another sign written fragile, and they would show you a piece of glass shattering or something like that. They would use symbols to ensure that they can communicate to everybody no matter what language they speak. Some of the things in chemistry, like this graph and this symbol here, it means the same thing to everybody. If you're doing chemistry, if you're writing chemistry in a different language, like in Chinese or in Canada or whatever, they will still use this sign for reversible. They might use something different for A and B, but they'll still use this sign for reversible. They'll still use this for the plus also. Okay? So these are universal symbols for us, and reversible, and then C on this side. So now, if somebody asks you, what is the energy change for the forward reaction? What's the word we said? Exothermic, right? Because reactants have more energy than products.
Yeah.
So now by the time reactants have become products, some extra energy here is lost. Now we have put a symbol, we've been putting a symbol next to this reaction. What is that symbol? With the triangle.
Change.
The change in heat energy.
Yeah.
We are putting a sign in front of that symbol also. What's the sign that we are adding?
The delta.
Plus.
Yeah, no, but we are putting delta H. That's for the change in heat energy. But do we put something in front of the triangle if it's exothermic?
Oh, the arrow.
No arrow.
Is it the subtraction sign?
Yes.
Okay.
But the subtraction sign, is that making any sense to you? Something is giving off heat.
So heat is released, that's why.
Negative increase.
Negative increase?
Like it's losing heat.
It's losing heat.
Negative.
Say it, Manan.
So the heat is released. So
It's negative.
there's a fall in temperature of the particles, the heat energy of the particles.
Right. So then let's say that the system here has lost some energy to the surroundings.
Yeah.
That's why the negative, right? So sometimes it's difficult for us to understand that, because normally when we say something is releasing heat, our brain naturally thinks that's positive. You know, because temperature is going up, so we put the positive sign for that, right? And then we say something is taking up heat and it's getting cold, then the surroundings is getting cold, then we would think the negative sign goes for that. But that's why we have to make sure we train our thinking, our brain, to not get that confused in chemistry. And it's because the place where the reaction is happening, inside of that space, heat is sent to the outside. Because reactants have this energy and products have this energy, right? And as you go down, where is that energy going? That energy is going to the surroundings. That energy is going to the surroundings. It's sort of like if you drop a huge rock from the 10th floor of a building down to the ground.
It creates a vibration.
It creates a tremendous release of energy.
Potential energy.
Right, that would be sound energy, and if it's water, you have a huge splash and all of that. That gets released to the surroundings. But now the system has now lost all of what it has.
Yes.
It can't do it again. It's lost all of that energy now. So that energy is lost to the surroundings, and that's why we put the negative sign. On the other hand, suppose we wanted, after you've dropped a huge block of metal that doesn't break, you dropped it to the ground from the 10th floor to the first floor, and then you want to go back now. From the ground floor, you want to take that block of metal up to the 10th floor, and you don't have an elevator. I mean, you could do it with an elevator, but I want to say we're doing it without an elevator because I want us to think how much hard work we would have to put in to pick it up and lift it and move it up back to the 10th floor again to repeat the procedure. We'd have to be doing all of that work, which is to be moving that block which has got a force and it's being pulled by gravity, and to move it a certain distance. Manan, you're taking physics.
Yes.
Work done is equal to force multiplied by distance moved.
Cos
So,
theta.
Right?
Cos theta.
Cos theta.
Right. And cos theta also, right? So therefore now you'll have to take it all the way up. You're taking physics also, Aditya?
Yes.
Right. So you've done this topic also then physics, right now? Right now it's going on.
No, it's finished.
It's finished.
Yeah, now we're doing electric field.
Right. So now you'll have to take that energy. The point is, now when a reaction, a chemical reaction is taking that energy, it's not like us picking up a block. But what we notice in the surroundings is that the surroundings have to provide that energy. And as the surroundings are providing the system with that energy, our thermometer is going to show a fall in temperature. So the same reaction now, if we consider it as C reversible going to A plus B, then we would have a positive delta H. Right? This means, what's the word for this? Endothermic, and the word for this? Now people use various little things to help them. Endo, and we can change it from endo in the spelling to help us. We can think of it as Indo, because energy taken in and the system gets cold. And well, the other one, exo, that's the one. That's just going to be the other one in any case.
Yeah.
Once you have something to help you remember one, when it's two things like this, right?
Yeah.
Then you can figure out. So endothermic or endothermic, if you want, energy taken into the system. The outside becomes cold. We should also have cold, because that's what we will experience if we are carrying out the endothermic reaction, right? You guys carried out the endothermic reaction. You experienced that your beaker became cold with the ammonium nitrate. And then the other thing was the sodium hydroxide. Did you feel the beaker becoming hot for the sodium hydroxide? Did you feel any warmth actually?
Yeah.
You felt some warmth because the temperature change was about 4 or 5 degrees Celsius. 6 degrees Celsius, right? So this is our exothermic and endothermic reaction. So now you have this reaction going on, and we say it's reversible. So let's get some data now from our simulation. Let's get the reaction to happen. But notice where we are keeping the temperature. From what you are seeing there, Aditya, you don't have your iPad, so let me ask you, what temperature you think this is? Is it set at a low temperature or a high temperature?
0.
It's set there, well, according to that scale that they have, right?
Yeah.
It's 0.
Yeah, it's 0.
So it's not pretty hot, it's not too hot. Now we're going to put 100 molecules on the A side. So we're going to put 100 on each side. Do you guys think when we are doing a chemical reaction, 100 molecules is a reasonable amount to say is reacting? You think any reaction we can do, we can measure 100 molecules and just say that's what we're doing?
No.
Why not that, Vidya?
Because realize that a lot of molecules, this is just a simulation.
Correct. Do you have any idea how, if I said 100 molecules of ammonium, how many moles do you have? Is it possible for you to calculate?
Yeah.
What would you do?
divided by the Avogadro's number.
Divide by the Avogadro's number, and you know how big the Avogadro's number is.
Yeah.
6.02 by 10 to the power of 23.
Yeah.
So the moment we are just talking about 100 here, let me get both sides. That side is
Well, actually, you keep on changing.
yeah, I know you will keep on changing, but I want to get it at some starting point, roughly 100 each, right? Roughly 100 each, and it will keep on changing. Yes, this keeping on changing thing is very important for us to really understand what's happening in a reaction, because very often when we see reactants becoming products, we think that reactants are put in there and they become products, and then once something becomes products, they can't go back to reactants.
Yeah.
But are you seeing different here now? Once something has become products, if the reaction is reversible, right? When something has become products, could it possibly go back and become reactants?
Yes.
Yeah.
Yeah. So that it's reversible.
It's reversible. So it means that you're thinking that you want to react A and B and to get C. But while you have a certain amount of C initially, and you think, okay, I've gotten my products, the next thing is you could end up having all of it go back and form A and B.
Yeah.
So if you're doing a reaction, you would want to know that, is there anything you can do to make this system where A is going to B go in the direction that you want it to go in? If your purpose is to make B, well, you want it to make B, right? Is there anything you can do or learn about that you can control so that when you're doing reactions, like if you're a chemical engineer and you're trying to do a reaction to make something, and B is the thing you want to make, then you don't really want it going back to A.
Yeah.
So this is where our understanding of this topic, starting from exothermic reactions, endothermic reactions, the Boltzmann curve, which we are going to go back and take a look at before we come to talk about this in a minute. And then this thing here, which is an energy profile diagram for a reversible process. Right now, something is happening here since we started. What's that observation? Look at the numbers. Asna, you have yours running?
Yeah. It's
What are your numbers saying to you right now?
51.
51 on, I'm guessing it's on the A side.
Yes.
And what on the B side?
Actually, it's fluctuated to 47 on the
Right,
other side.
it'll keep fluctuating, but right now it's around 40 something, and the other side is going to be 100 and something, right?
No, other side is 57.
What did you start with on either side? 50-50
I was 46.
on either side.
Yeah.
Well, okay, you had a smaller number there, but that's right still, because one side has gone to 60, the other side has gone
Should
down.
I increase it?
No, it's okay. Manan, what's your numbers?
101 on the left hand, 125 on the right.
So you started with more than 200 actually,
Yeah.
right? Now I started with around 100 each. Easy to track, and you notice here what's that saying there, around 60, and this is around 140. The particles haven't gone anywhere. We can't destroy the matter. The matter and energy cannot be created or destroyed, so the more matter is coming on this side, less matter on this side.
Yeah. No.
Right? So therefore now, with this low temperature, it seems as though the reaction is in a way where this side products are being formed more than reactants are being formed. I don't think it's going to change very much right now. And if I tell you that this is not going to change very much here right now, there's a word for this when the reaction reaches that stage. After you've mixed everything and you keep the temperature at a certain amount, and you realize products and reactants don't change, they just stay like that. The reaction is said to be at a certain point at that stage. What do we call that? There's a word for that. Anyone's heard this word before? Because I haven't given it before. Begins with E. Anand, you know the word?
Equilibrium.
Yes. It's equilibrium. Now, again, this is another word, like one of those things that we have a certain picture in our mind. So if I say equilibrium, does that mean that molecules on this side are at the set, they can't go back on this side, and molecules on this side, they can't go back on that side? They're
It
not.
doesn't mean that.
Does it mean that the concentration of chemicals on this side is the same as concentration on that side?
That it's balanced. Yes.
So then from the word equilibrium, we have a kind of feeling in our mind that it's like a balance, a seesaw balance. The mass on this side and the mass on that side are the same. Because that would be like our big world that we can see with our eyes. That's how we think of balance or equilibrium. But if I'm telling you though, Aditya, that this is equilibrium, this is now at chemical equilibrium, is it supporting what we just said or not?
No.
Because why is it not supporting?
Because there's a difference. It's not in balance.
It's not in balance like that.
Yeah.
But therefore there has to be a different meaning for what chemical equilibrium is. What is that meaning?
So quantity remains the same. Like
The quantity of what you have here and here remains constant. But does movement continue?
yeah, movement does continue.
Movement continues. So therefore something has to be the same. Again, the quantity of the amount of molecules, their concentration remains constant. What else is the same? It's another thing. Temperature is constant. The rate at which this is going here, the rate at which it's coming back here has to now be constant.
Yeah.
Because if it weren't constant, then the amounts would start changing. In the beginning, when we put 100 on each side, that's how we started them off.
That was like equal.
Right? That was not equilibrium. That is what you thought equilibrium was in the beginning. But look, it has changed from there now. And
Yeah.
it's come to this new point.
It's chemical.
This is your chemical equilibrium now. Previously that was just like a balance in equal amounts, equity or whatever. And that is because, again, in chemistry we get confused because you talk about equity, parity, equality, balance. Even in physics, getting something to balance on both sides with a little something in the middle, right? All of those things are not the same as chemical equilibrium because the rate of the forward and the rate of the reverse are equal. But the amount on this side and the amount on this side, not the same. Suppose it is that we wanted to do something so that we could get even more things coming on this side.
Will heat up.
You will heat up. You will, what do you think you will do with it? You will heat up. If you wanted to get even more things coming on this side.
Yeah.
Asna?
Yeah, to increase the reaction rate, you will heat up.
Right. Right. You guys all agree with that answer?
Yes.
Heat up. Now, when you heat up, you think it's only one side will get excited, will get kinetic energy.
No, both sides will get.
So that when the heat will only help the side that you want,
Yeah.
it wouldn't help the other side.
Because it flows from higher temperature to lower.
Think about that. Wouldn't the heat and molecules, do they know you or something like that? That they'll only one side will get the heat and the other side. Isn't that when you heat the system, both sides will get energy?
Yeah.
So therefore, how is that going to push the equilibrium in the side that you want it to go to? I don't know if people are getting lost with that, right? How is it going to put this push things towards B? Wouldn't B also have more excitement, more kinetic energy, and they would also have a chance to come towards A? Don't you think so, Manan? So it might not do anything, but it will do something actually. And the thing is, it will do the opposite of what you guys are thinking. But how it will do the opposite, this is what I want you to understand. Now here we have two temperatures. This is another thing that's confusing for people. You just show this graph to people, you ask them which one is dealing with the higher temperature, what do you think they'll go for?
Which one is?
Which one is the higher temperature, T1 or T2? T1 is not the higher, right? T1 is the lower. The
Yeah.
number of particles is on this side, the kinetic energy is on this side.
Yeah.
Now,
Yeah.
didn't we say already that temperature is the average kinetic energy? So this is like, if we think about it as a class and their scores, this is the scores on this axis here, right? And this is the number of people who got that score. So in class T1, which is the lower class, a lot of people got this low mark,
Like 2, 3, yeah.
right? And a few people got higher marks, the red,
Collectively, T2 is high.
right? In class T2 now, a lot of people, the majority of the people got around this mark here, and a bigger chunk of people got higher marks. So the distribution of the energy, because you know kinetic energy is about taking the energy of all the particles, temperature is about taking the average kinetic energy, I should say, of all the particles. So you could have some particles, even though it's T1 and it's a low temperature, you could have some particles that have really, really high energy still. right? Still that possibility. Just like in the low performing class, you could have your top student in there. But in T2 now, more particles are going to be with more energy in T2. So if it is that our reaction profile, how does it look like again for the exothermic? Looks like this, right? And you have the barrier and you have this.
Heat is lost.
And then you have some things on this side and you have some things on that side.
Yeah.
Okay. And then we give higher temperature. The energy barrier that this side has to cross to go over on this side, is it bigger than this energy barrier from this way? The barrier that they have to cross, which is this. It's all of this energy that this side has to go over, right?
Yeah.
But going from this side, is it even more difficult?
Yes.
Yeah.
It's all of this energy
Yeah.
that they have to need to cross. So therefore, if energy levels are low in your system, then it's because that's what low temperature is in our simulation, right? If energy levels are down low, which side is going to have the advantage in this battle?
The left side.
Why so?
Because they need less energy to escape to the other side.
Right. So then remember the question I asked earlier. If you are a chemical engineer and you want to get your system to go from what to what, let's go back on the simulation. The temperature is low, guys, and we started 100 each and everything is coming towards this side. And then you said if you increase the temperature now, right, that more things will come on this side. Right? Right now the temperature is low, and after starting them off at the same, this side is seeming to have an advantage because of what?
Because they need less energy.
Because they need less energy. So now if I decide to put more energy inside there for everything,
Yeah.
But we
That also
give
have
enough
an
energy so that it doesn't pass over.
right? If I give more energy, a little bit more energy doesn't matter. Once I give a little bit more energy
To which side?
to both sides, you can't only give energy to one side. You can't go in a chemical reaction and say it's not like two armies battling against each other and you go and you help that other
Yeah.
side.
Yeah.
You could think of it like that, but whatever help you give, both sides will get it.
Yeah.
So suppose we gave a lot of extra energy now into the system. Which side would really benefit from that if they're battling against each other?
The right side.
Why so, the right side?
Because they needed like extra energy to get, and they'll get that.
They need extra energy
So that like they are in disadvantage.
they need extra energy to go over the barrier.
Yeah.
Now we would like to make connections between all of this talk and the Boltzmann distribution curve. Now, one of the things we are focused on doing is letting people have proper understanding of what it is we are doing. Because on this video, as you go through, you will see in the IB examinations, they'll ask you to sketch the Boltzmann distribution curve. The students will remember that you put kinetic energy here, this here, you put two curves, you label everything, and they score 4 marks out of 4. And still they don't really understand what the meaning of this curve, right? So we want to really get the understanding of this curve, and that's why I put this thing here, because this thing is connected to this thing. Reactants is trying to become products, right? Reactants are trying to come to products, and right now we have a low temperature. When we have a low temperature, then reactants don't have such a big barrier to go over. So they can make it because it's like you don't have that much energy needed to climb over. Both sides have same amount of energy really. You can think about like robots on each side, a robot army on this side and a robot army on this side. The reason I say robot is because we can make all of them identical. Okay? And then we give all of them the same battery power. And we say, go ahead and try to climb over the mountain. This side will have an advantage. But suddenly now, let's just see why that is so.
We increase the heat for the system, and we increase so much that then kinetic energy increases this much. So it will still have an advantage, right? This side will still have advantage to go over there because they will still increase this much, which will not cross the barrier.
Correct. Correct. Both sides.
But still some of the particles would go.
Yes. Correct. What you're saying, correct. Now, let's talk about T1 now. When temperature is low, the side going forward, look here, I put activation energy, right? Activation energy is this thing here, the barrier, right? Which side has the lower activation energy? It's lower activation energy is the one coming this way.
Yeah.
And then the one going that way has the bigger activation energy, right?
Yeah.
So, if temperature is T1, things that have this activation energy, let's call it number 1. Let's say this is activation energy. When we go up and we join here, it means that everything on this side of the graph, all of these particles will be able to cross the barrier because they have more than the energy, more that's needed, right? But coming from this side now, the energy is so much bigger.
Yeah.
So only a much smaller amount, you'll have to go like here and then go same to the T1 graph, go across and then realize that, well, it's only this area.
Yeah.
Then when we decide to make it T2, as Manan is saying, both sides will benefit,
Yeah.
but the difference now will be a little bit more in favor of this side. Because which side will get more benefit, you know? If
So
you
that's-
uplifted the level on both sides, remember this side is always probably already finding it easy. Because the battery that they were given in their engines or to power their robots was already sufficient.
Like the difference in energy between the reactants and the products, reactants will obviously have more, but the products will get that extra edge to go over the
Right, you'll get that extra edge now to have more of them. Now the data on the Boltzmann curve will show that.
Yeah.
Suppose now we considered what we saw from the first T1. Now the second temperature T2, if we go back to the same points, this original one, all of these particles here, when we hit this point, now we're looking at the blue graph, right? Everything on this side of this blue graph here would, so all of this here in the curve would be able to go over the activation energy. And then for the other one, all of this would be able to go over the activation energy. But if we compare it, when this one has moved to T2, it's all of this extra help it's getting here. Right? So the one that has the bigger barrier to cross, and I understand that all of this kind of stuff that we're showing here could be confusing, even though I'm recording it. Okay? So that's true. But the bigger barrier is on this side, on this side to this side. So it's sort of like, let's take an analogy, but analogies can always break down, you know. So suppose you already had like 10 crores rupees already in your bank account, okay? And another person had like 1 lakh rupees in their bank account. 1 lakh. And these two people are now going to have, these two armies are going to battle against each other. And I say that I'm going to give each army the same allocation of money. I'm going to give each army 10 lakh rupees. Which army would be so happy to get that? Because they are getting 10 times more than what they ever had. The one who had 10 crores will say, go away with your money. Right. That's from the human point of view. In the system like this now, it's like that. Because the barrier on this side, Anand, is not so big. So you rightly said it will go up.
Yeah.
But going up when they already had the energy to go across in any case. But this one now, the proportion of particles that would be elevated would make it significantly improved. So that what we will say is that when you increase the temperature, which side benefits more? But look at what's happening now. You see, everything is so much energized that, well, the barrier doesn't really matter anymore now, right?
Yeah.
You know, in the sense that everything's got that equal chance to cross pretty much.
Everything just coming to this side.
So the right side got more advantage, right?
So,
Because they can go back.
well, the right side will always have more advantage. But what, in the beginning when everything was low, right?
The left side had more.
Yes. So right now, for example, that's, again, we could take an example. In India right now, rich people have a huge advantage over poor people, right? But eventually, suppose quality of life in India is that the economy gets bigger and bigger and bigger, and poor people are less poor, okay? Then, as India is getting more and more money, how much benefit is rich people really going to get from that? They already have so much. The people who are really going to feel the benefit are the poor people who are struggling every day to make ends meet. As the country gets better off, they are the ones who will benefit. And that's what we have to have in our minds. Yes, you are correct. Manan, to say that both sides are getting tremendous energy. And it's not like in these reactions, people say that we'll be looking at some different ways and we are going to miss the understanding. Both sides are going to get kinetic energy.
Yeah.
And they're going to get tremendous excitement because they're getting the same temperature, energy of motion. But which side is seeing the advantage in terms of this balance to go over from one side to the next?
Products.
This side, look at the data showing that. If you were a chemical engineer and your job was to squeeze this side down as much as possible and don't ever let it get out of there, what would you want to do with temperature?
Decrease.
Increase it. You would decrease it. Asna, you're correct, you would decrease it.
Because you don't want the other side to get enough
Yeah.
energy so they can come back.
Right. Now, Manan, you're still saying increase, so I want you to be happy that why you're wrong with that. Because if you're a chemical engineer, Manan,
So if we decrease, it will just come back with the flow and it will just stay there.
No.
right now the temperature is low. You could leave your simulation like this here now. If we leave this and we come back after lunch, you will notice it will come back that this side will have more and this side will have less. It's going back there already, right? Because the low temperature means that it doesn't take much energy for this one to come over here. But you're keeping temperature really low so that this side will remain struggling to have a chance to get over here.
Yeah.
That's what you want to do. And the lower and the lower and the lower that you keep that temperature, the more you will get your yield, as they say, coming over on this side. Okay, so I'm sure, did you guys learn about Haber process and had to memorize that at any time for your board exam?
Yes.
You did?
Yeah.
And that the low temperature is what favors the forward reaction to get the ammonia. But if you are an engineer working to make ammonia, you can't put the chemical plant in a freezing place and expect to get enough ammonia.
So like we got to put in enough energy for the reactants to become products, but not like over so that the
Yeah.
products can also have
Yes,
enough energy.
so you have to get that compromise, that place. I mean, as Manan keeps saying, the more energy you put in, the more both sides will get excited. But you don't want both sides to get excited so much that, because it's a reversible process, right? So you have to try to get a point where you are going to squeeze this side and not give it sufficient energy to get over, but you're only going to kind of cheat for this side because they have a shorter barrier and let them get over the barrier. And this is why the forward reaction, we are going to say it's favored by what type of temperature?
Lower temperature.
And the reverse reaction is favored by
Higher temperature.
higher temperature. And that's what we have to get, really. And this whole thing here is good. It's what we call the understanding of what's happening.